Thank you very much for being here, all of you. We're here for the PhD defense of PhD candidate Stanislav Chernyshikhin, who's a student with supervisor, is Associate Professor Igor Shikovsky in the doctoral program of mathematics and mechanics. And he will talk to us. I will let him present this title and the detail. Well, for me, briefly, I'm Dean of Education here, a professor at Caltech in the Center for Digital Engineering, and I was president of research. I've done a lot of work in research and education in aerospace and mechanical engineering at École Polytechnique of Montreal, and created a spin-off company and sold it to an American company in the field of product lifecycle management, and I'm a fellow of the Canadian Academy of Engineering. Great. So Professor Igor Yadrovtsev from the Central University of Technology in South Africa. And Professor Yadrovtsev is a researcher with more than 38 years of academic experience in the field of applied optics and laser technologies. The research interests of Professor Yadrovsky are related to additive manufacturing, selective laser melting and sintering, laser processing, and material science and optics. So Professor Yadrovtsev has broad experience in implementing laser powder bed fusion in industrial application and was head of the additive manufacturing department at LLC Roussel. Professor Yadrovtsev is a leader in the field of development of additive technologies for medical application in South Africa. And since July 2021, Dr. Yadrovtsev has been a visiting professor at the Faculty of Engineering, Built Environment and Information Technology of the Central Technological University of Free State in the Republic of South Africa. He has an H-index of 47 with 11,000 citations and more than 200 papers. Then another external member, Associate Professor Alex Volofsky, University of South Florida in the USA. Alex Volofsky received his PhD at the University of Minnesota in Material Science and Engineering. At this moment, Alexei Volofsky is an associate professor at the University of South Florida in Tampa and Department of Mechanical Engineering. And Professor Volofsky is teaching courses in material selection and mechanical design, advanced material, mechanics of material, introduction to material science, and applied elasticity. The research interests of Professor Volofsky are related to thin films processing, mechanical properties and characterization, adhesion and fracture of thin films, microelectronics and MEMS reliability, irradiated material properties, and X-ray diffractions. He has a broad experience in research related to industrial application. He's been working in such well-known companies as Motorola and European X-ray free electron laser. And Professor Volofsky has an H-index of 55 and with 13,000 citations with over 500 papers. Internal now jury members, Associate Professor Ivan Sergeyev, Director of the Center for Manufacturing Technologies, or Material Technologies, I'm sorry, Ivan, Material Technologies. Received his PhD in solid mechanics in 2013. And Dr. Sergeyev has been a fellow of the Civil Research and Development Foundation for Basic Research and Higher Education Project in the States. Professor Sergeyev worked in Nizhny Novgorod State University, Mechanics Research Institute, Dynamic Testing Laboratory, and also at the Boeing Company. In 2005, Dr. Sergeyev visited Bordeaux University, France, the LAME FIP laboratory as an invited researcher. And Dr. Sergeyev joins Caltech as an assistant professor and head of the Laboratory of Computational Engineering and Mechanical Testing. And today, he's the director of the Center for Materials Technologies. The research interests of Dr. Sergeyev are related to experimental analysis of mechanical behavior of material, experimental verification of deformation and fracture models for additively and traditionally manufactured metals and alloys. Professor Sergeyev has an H-index of 12 and 455 citations with more than 50 papers. Our next internal jury member is Assistant Professor Stanislav. He defended his PhD at Moscow State University in 2014, and Dr. Ivlashin joined Skoltech in 2017 and significantly contributed to the research of additive manufacturing materials and technology in the Center for Material Technologies. Dr. Ivlashin has been an assistant professor at Skoltech since 2022, and the research interests of Professor Ivlashin are related to multiple fields, namely structural properties of high entropy alloys produced by selective laser melting and direct energy deposition, in situ alloying of material, and printing of gradient material using DED, printing of metal matrix composite using the SLM and DED technologies. And Dr. Ivlashin conducted research on mechanical, thermal, magnetic, and corrosion characteristics of 3D printed alloys. Professor Ivlashin has broad expertise in electrochemical characteristics of nanomaterials modification, and the development of material processing. Stanislav Ivlashin has an H index of 22 and over almost 1,500 citations and 139 papers. The supervisor now is Associate Professor Igor Shikovsky. In 1992, Igor Shikovsky defended his PhD dissertation at the Lebedev Physical Institute. Professor Shikovsky is a specialist in the field of laser technologies, physical metallurgy, and methods of numerical modeling of physical processes. Professor Shikovsky worked at the Samara branch of the Lebedev Physical Institute from 1982 to 2018. In 1993, Dr. Shikovsky started experimental work in the Laboratory of Technological Lasers, where he became one of the initiators of a new direction in laser technology, additive synthesis of volumetric parts, which is 3D printing. Since 1995, Dr. Shikovsky has headed the research group on additive technologies and defended the dissertation of Doctor of Physical and Mathematical Sciences in the field of chemical physics. In recent years, Professor Shikovsky was the head of the additive manufacturing laboratory at Skoltech. He has an index, H index of 31 and 35, almost 3,600 citations and 240 papers. Before we start the presentation itself, I will introduce our candidate, PhD candidate. Stanislav Chernyshikhin participated in a double diploma master program between École Nationale d'Ingénieurs de Saint-Étienne in France and the National University of Science and Technology, MISIS, from Moscow. The master programs were related to additive manufacturing technologies and material science, respectively. In 2022, Mr. Chernyshikhin participated in the Skoltech Orlikon joint industrial project on the assembling of laser powder bed fusion installation. During his PhD study, Stanislav participated in a related scientific project funded by the Russian Foundation for Fundamental Research. The PhD research gave a foundation for the startup idea of printing NiTi endodontic files. Further development was done with the support of the Skoltech Translational Research and Innovation Program, and Mr. Shikovsky has an index of 6, an H index of 6 with 92 citations and 25 papers. So the way we'll proceed, we will have a presentation from the candidate for a maximum of 40 minutes. Then we'll have a period of questions. We'll most likely go 2 rounds of questions in case, and then we'll have also the audience. We have some famous professors in the audience, so it will be good, and online too. And after this, we'll have jury deliberation and the decision. So please go ahead with the presentation, and we are listening carefully to you.
Thank you for this introduction. My research dedicated to tailoring or the functional properties of nitinol during laser powder bed fusion process. I want to start my presentation from a small introduction dedicated to shape memory effect and the superelasticity. So nitinol is an equiatomic intermetallic alloy in the nickel titanium system, and there are 2 thermodynamically stable phases, martensite and austenite, for low and high temperature respectively. And this phase transformation occur at relatively low temperatures, and with this transformation, shape memory effect can be explained. On this slide, we have a diagram with stress, strain, temperature coordinates, and at the initial state, our material nitinol is have a martensite structure with twinned with a microstructure presented by twins. Once we load our material, the deformation accommodated by the twinning process, so no plastic deformation. And once we unload our material, we still have some residual deformation as it is for conventional materials. But once we increase the temperature above some critical point, namely austenite finish temperature, the transformation from martensite to austenite occurs. And during this transformation, we have rearrangement of the lattice of atoms, and during this rearrangement, actually the macro shape also recovered. So what happens if we try to load our material already above the austenite finish temperature? In this case, at the initial state, we have austenite phase, and during the loading, the deformation accommodated by the transformation by so-called stress-induced martensite. And finally, we also in the end, we have detwinned martensite microstructure, and as far as we are already above the austenite finish temperature, after unloading of the sample, we immediately go back to austenite and with subsequent macro shape recovery. But also on this slide, we can see the fundamental dependence of mechanical response of the shape memory alloy from the transformation temperature. So if we load our material at the ambient temperature below martensite finish, we observe shape memory effect. If we load the material above austenite finish, we have superelasticity. So both effects are used in real industrial applications, in many industrial applications, and some of these applications can be more efficiently manufactured by 3D printing. So in literature, there are already some potential applications of 3D printing of nitinol devices. So on this slide, we can see stents for coronary vessels that are often manufactured from nitinol. Also, we have idea to 3D print nitinol implants as far as stress-strain curve of nitinol in the superelastic state is close to the real bone. And finally, we can match the mechanical properties by introducing the porosity to implant. But at the present state of the art, there is a problem of manufacturing the nitinol components, nitinol devices with 3D printing with laser powder bed fusion. And this problem is related to the change of chemical composition after the laser powder bed fusion consolidation. So in many paper works, it was demonstrated that after this 3D printing, the chemical composition, nickel content, was reduced. And this circumstance in turn lead to the shift in the transformation temperature. So there is a well-known dependence of the transformation temperature from the chemical composition. And this dependence was verified many times by many authors in different papers, so we can rely on this dependence. And this is telling us that by changing the chemical composition of alloy by 1%, we have shift in transformation temperatures by 80 degrees, which is quite a lot for any application that I mentioned. So for example, if we want to 3D print a stand for coronary vessel, we need to have transformation temperature just below the temperature of human body by degree C. So we want to have the exact transformation temperature. But for now, we only can measure this transformation temperature after the manufacturing. So based on this, the main research aim is to study the relationship between the material properties of nitinol and laser powder bed fusion process condition. For this task, different samples were manufactured with laser powder bed fusion, and then they were characterized by various techniques such as mechanical tests, phase composition analysis, and transformation temperatures measurements. So in our laboratory of additive manufacturing in Skaltech, we have TRUMPF TruePrint 1000 installation that was used in the experimental study. This machine have nowadays classical system based on 3 cylinders inside. So one cylinder is for the powder storage, another one includes the substrate or building plate, and the third one for the excess of powder. And the final part received by repeating the same cycle. So we depositing the powder on top of the substrate, then laser scan this layer and remelt it. Then the substrate goes down, and this process repeated again and again. In the experiments, a spherical prealloyed nitinol powder was used. Prealloyed means that each particle inside the powder is an alloy itself. It's not the powder is not a mixture of nickel and titanium powders. It's important to receive homogeneity in our samples and to provide reasonable metallurgical bonding between the substrate and samples. And in-house built nitinol substrate was manufactured. And for the study, a relatively broad window of process parameters was utilized. It showed here in scanning speed laser power coordinates. And the first step of the experimental study involved single track analysis. At this step, the substrate was lowered by 1 layer thickness. The powder was deposited, and then it was remelted with a single laser passage. And during this analysis, some process parameters were already excluded as far as they do not provide enough remelting depth. When for other cases, the melt pool dimensions were measured, so namely width and depth of the melt pool. This data will be used further. And for second step, thin-walled samples were manufactured. I want to spare a couple words to the concept of thin-walled samples. So the basic idea behind it to exclude the influence of the hedge spacing parameters, to exclude the influence of the adjacent tracks. So here, for a single sample, we have only 1 laser passage per layer, as it showed schematically here. So all samples were placed between 2 stiffeners to exclude any possible distortion during 3D printing. And after the manufacturing, these samples in one turn were cut by electrical discharge machine to receive the samples for further mechanical tests. And mechanical tests were performed within two schemes. First tests were run until fracture. It was done to evaluate what will be the maximum strain that we can achieve in most of the sample. And the second test was actually a single cycle loading. That means we load all samples to the same strain to evaluate what will be recoverable strain. And after the first test, after the fracture of samples, the results show that we can subdivide all samples by two groups. So first group involved the samples that were manufactured with low linear energy density input, and this result in the generation of defects because of lack of fusion. So in this case, we had crack generation and propagation from void to void, and the overall mechanism of fracture was brittle. When enough energy density input result in the ductile mechanism of fracture, when the surface fracture was represented by the cup and cone structure. Results of the second test are shown on this slide. So here we can see that samples manufactured by different combinations of process parameters result in different irrecoverable strain in the as-built condition. And if we plot this result as dependence of irrecoverable strain from linear energy density, we observe the positive trend, and after some critical value, it came to the saturation point. That means that for these samples, we do not have any recovered deformation because of the transformation, and all deformation here was recovered only by pure elasticity. And these results are explained by the differential scanning calorimetry. We can see on these DC curves that were separated by cooling and heating curves that all regimes caused shifting of the martensite and austenite peaks to the higher temperature. And interestingly, for the case of high laser power, we observe more rapid shift in this case. And again, we clearly see the dependence of the transformation temperature from the linear energy density. And finally, to prove that we do not have any short phases after the manufacturing of samples, X-ray diffraction analysis was performed. And here we can see that all peaks of XRD spectra are actually from the B2 and B19 phases. And based on the integral intensity ratio between all peaks, we can even evaluate the ratio of volume fraction between these phases. And also we have the dependence from the regimes. Finally, to summarize the results and to conclude, it was demonstrated that different process conditions of laser powder bed fusion may cause different mechanical response and different transformation temperatures. In this regard, a sample with 6 thin-walled parts was manufactured. Each thin-walled part was manufactured with one regime, and this sample was deformed in liquid nitrogen. Then it was placed on top of heater and was observed by thermographic camera. and the high resolution camera, and we can see that multi-stage shape memory effect activation appears. So each thin wall part recovered the macro shape by its own temperature. The second part of my presentation dedicated to numerical experiment, namely the simulation of the melt pool during laser powder bed fusion, and this was done to analyze more complex scanning strategies, because in the case of experimental study, we analyzed the simplest geometry, so thin wall, but in reality, we have some complex scanning strategies. So the laser passes shown here with green lines, and this scanning strategy rotate from layer to layer. So in this case, analysis of local shift in transformation temperatures will be complicated. So in this regard, the following simulation was performed, and the following procedures was done. So first of all, the simulation of single tracks was done to validate the model. Secondly, simulation of thin wall was performed to analyze the thermal history and evaporation dynamics. And finally, in thin wall, we calculated nickel content, or final chemical composition, that is coupled with resulted nitinol functional properties. All simulations in this work were performed in Kintec simulation software for additive manufacturing, or KISAM. So this solver was developed by Kintec lab, and this is a fluid dynamic solver based on lattice Boltzmann method. And this solver actually involve many important phenomena that happen during laser powder bed fusion. So first of all, we have powder bed. The energy deposition is done through the multiple reflection between particles and substrate. Then we have in the liquid domain Marangoni convection. Because of the temperature gradient, we have recall pressure that cause the deformation of liquid, and also we include surface tension for liquid and wetting of powder. Each simulation starts with from thermophysical properties, and there are some lack of data of thermophysical properties for nitinol that are required for the melt pool simulations, and some data was received experimentally. The most important experiment was done to measure the surface tension of nitinol melt. So this is method of pendant drop. Inside a graphite heater, the nitinol melt was formed, and from a graphite dropper, the drop was squeezed, and based on the measurements of the profile, the final value of surface tension was received, and it was used in the further simulation. So the first step of simulation is powder bed generation, and based on the analysis of layer thickness for the stationary process of laser powder bed fusion, a 45 micron layer thickness was chosen for the further simulation, and the particle sizes for this powder bed, they match with real granulometric characteristics of real powder that was used in experimental approach. And this step of simulation involves the single track simulations, and in this relatively wide window of process parameters, we can see both modes of melting, so namely the conductive mode of melting, when the melt pool is mostly spherical, and also a keyhole mode of melting when we have significant deformation of liquid and deeper penetration of laser and deeper remelting depths. Concerning the morphology of single tracks from the top view, we can see that for the lower linear energy density case, the morphology look the same, but for the highest energy density, we can see that for the simulation we received a ripple pattern, when for the experimental case we have a bead with a large height on top of the substrate, and this is explained by zero displacement condition that was applied for powder, but in reality we actually see the denudation effect when particles nearest particles to the melt pool, they are interrupted, they are moved to the melt pool and make the liquid domain bigger. And overall convergence between the simulation and the experiment presented on this slide. So we can see comparison between the width of the melt pool and depth, and the convergence is good. We have the highest discrepancy for the regimes where the transition from conductive to keyhole mode happen, and in this case it's complicated to calculate these parameters with required occurrence. So the second numerical experiment involved the simulation of thin-walled based samples, and the procedure look like in the experimental study. So we make the powder bed on top of the substrate, we remelt it with laser, then we on top of this geometry we add additional layer of powder and remelt it with the previous geometry. So this numerical experiment was run until we do not have any significant temperature rise at the substrate level. So the probe location is shown with red point, and in this point the temperature was measured for every layer, and we can see after 12 layers this temperature rise was insignificant. And these calculations actually was performed to analyze difference in the evaporation kinetics for nickel and titanium components. So we need to calculate the flux of vapor particles, and for this we need to know the activity coefficient of nickel and titanium. And this was done based on the thermodynamic approach, so we can calculate the activity coefficient from the partial Gibbs free energy. The partial Gibbs free energy was calculated from the total Gibbs free energy, which in turn is presented by Ridley-Kister power series, which is known in literature for nitinol for various temperatures and compositions. So the results are shown on this slide. So we have dependence of partial Gibbs energy for nickel in nickel titanium solution. Then we have activity coefficient, and finally multiply this coefficient by the concentration. We have activity that was used. And in this regard, we received such calculation in each cell of the performed simulation, and we can see two cases. So first one, this is case A. The thin wall was manufactured by the low energy input regime. And in this case, we can see that no shift in chemical composition appeared. So remelted volume have the same nickel content as powder and substrate, but actually in this case we can see even on this simulation some lack of fusion defect. So these samples have poor mechanical strength. From another side, concerning the case B, when the thin-walled sample have enough energy input, we can see that nickel depletion happened. And after so-called achieving of stationary chemical composition, after many remelting steps, the nickel content was measured across this line, and average value was used further. And such procedure was made for all regimes, and we can see the dependence of nickel depletion, from the linear energy density. And finally, to summarize all results of this work, we can create dependence of calculated nickel content that was calculated for different regimes. And also we can take experimentally obtained transformation temperature that was measured experimentally by differential scanning calorimetry. And this dependence, received dependence, is actually close to the dependence that I showed in the beginning, that was verified many times. So by this, we can conclude that the main mechanism of shift in transformation temperature or local adaptation of functional properties is the different kinetics of nickel evaporation that was calculated by this simulation. And the final part of my presentation dedicated to practical approach of this laser powder bed fusion technology for manufacturing of micro devices, namely superelastic, nitinol, and odontic files. These files are used in dentistry to clean root canals with irregular shape. So this file have complex geometry, and it can deform and adapt itself to the form of a canal. And some irregular shape canals is highly complicated to process without such instruments. And the samples of these files were manufactured based on the experimental data. So all regimes are presented again in scanning speed laser power coordinates, and we can see that from the top side we have a limit because of poor ultimate tensile strength. From the other side we have low resolution limit, and finally we also have a region where significant increase of transformation temperatures occur. And finally, with green point, we have optimized regime. And these samples were received. We demonstrated that we can achieve enough resolution to print such files. And now this project is at the stage of mechanical tests also involving some deleted teeth. All main conclusions of this research are presented on this slide. So critical relationship between nitinol properties and laser powder bed fusion conditions were obtained. Then 4D printing feasibility was implemented experimentally by introducing a multi-stage shape memory effect in a single sample without any additional heat treatment. Then self-adjusted files were manufactured by high-resolution laser powder bed fusion, the enough resolution was achieved for this instrument. Then some thermophysical properties were investigated with emphasis on the simulation of the melt pool. So surface tension value was received. And finally, by summarizing the experimental and simulation result, it was demonstrated that the main mechanism for tailoring of functional properties or shift and transformation temperatures are related to the different evaporation dynamics for nickel and titanium components. So main publications are listed here. We have four publications directly related to this research, and also during PhD there were other publications prepared. Also main results were performed on a number of international conferences that are shown here. And finally, I want to thank my family for support. I want to thank my supervisor, Igor Shishkovsky, for all the knowledge that he gave to me. I want also to thank my colleagues from National University of Science and Technology, MISIS, my colleagues from Kintec Lab and from Polytechnic University. And finally, I want to thank the program of Skaltech Translational and Research Innovation. They supported this idea of printing nitinol files, and the project was further developed with the support from these guys. So thank you for your attention. Please, if you have any questions.
Thank you very much, Stanislav, for that presentation. Very good presentation. We will now go in the round of questions. First to the jury members. So we'll start with Professor Igor Yedrotsev, please. And like I said earlier, there is a possibility also to come second time around if necessary. Professor Yedrotsev.
Okay, dear colleagues, thank you for giving me this opportunity. We several times talk with Stanislav about his presentation, about his work. I'm very good know this work. But for Stanislav, I have only one question. We talk without him about a lot of time about the volumetric energy density, and I would like ask him again about what he think about this parameter and how we can use this parameter in our works.
Yes, thank you, Professor Yedrotsev. As we discussed, in this work, I use linear energy density to kind of compare the regimes between one and another. But actually, as was discussed, in some cases, we can see that the same linear energy density, which in this case is P to V expression, it's not fully describe the regime of the manufacturing. So in this case, we can see that even for some close values of linear energy density, we have a completely different behavior of the transformation temperatures after the consolidation. So for example, if we speak about the higher laser power, we can see a much more rapid shift in transformation temperatures. So I would say that linear energy density and volumetric energy density should be used carefully, and also the regimes of melting and manufacturing should be discussed both in the process condition versions, so laser power, scanning speed, layer thickness, edge distance, and also additionally it can be presented as a linear energy density or volumetric energy density.
Mm-hmm. Thanks a lot for your answer. And also my second question, it's not concern NiTi node, but maybe more about processing LPBF. What do you think? We can use keyhole mode for producing LPBF part.
Again, if we speak about keyhole mode, there can be regimes when the keyhole mode just started, so the deformation of liquid appeared and the remelting depths increased, but there is no intensive evaporation happening. So such process conditions can be used carefully for production of real parts. But concerning the case when the intensive evaporation occur, the keyhole mode regime of melting will cause so-known keyhole porosity or gaseous porosity when some gas bubble was trapped inside the liquid melt pool, and then it was solidified, so we received a gas of metallurgical pore inside our material. So these regimes are not really for the real-world applications, I would say.
Okay, thanks a lot. For this time, I'm thinking I'm done, and please, we can ask other G for questions.
Okay, thank you. One question to you: are you satisfied with the changes that Stanislav made to the answer to your comments for the thesis?
Yes, completely.
Okay, thank you very much. Now we'll now go to Associate Professor Alex Volinsky. Please go ahead with your questions.
Yes. You reported on slide 17, I think you reported the mechanical properties of the nitinol that you printed, but you reported that in terms of the force versus strain. Do you have any idea what would be the corresponding elastic modulus of the material that you printed?
Yeah, we can plot not the force against strain, but calculate stress against strain, and in the elastic region of the stress strain curve, we can calculate the elastic modulus, and based on the phase that is in the material at this condition, we can have different elastic modulus. So if we have a mixture of phases, the elastic modulus can be in between of the value for austenite and for martensite.
Right. Do you have any idea of what the modulus would be that you measured?
Sorry, I didn't hear. Repeat.
Do you have any idea of the physical values of the modulus that would result from your measurements?
Yes. So for austenite, the modulus is 40 GPa, and for martensite phase, as I remember, it's lower. It's about 10. So for different samples, I received slightly different results in between these values. But I didn't made emphasis on the elastic modulus in this study because I was mostly interested in irrecoverable strain after the single cycle deformation of these samples.
Okay. Do you observe any size effects in the structures that you 3D printed for endodontics applications?
Yeah, this is good question. So the size effect in terms of mechanical tests for nitinol, they appear in the case when the grain structure at the surface area of the cross section can be so it's dependent on how much grains do you have in the cross section. So if you have just a few grains, so if we speak about some micron wire, for example, micron nitinol wire, we will have the size effect, so the stress plateau on the stress strain curve of nitinol, it can be shifted as it is dependent, as it will be dependent on the diameter of the wire. So we have different number of grains in the cross section. So that's why this stress plateau will be different. But in my case, I have a strong texture for all my samples manufactured by different process conditions. And in this regard, also, I do not use wires, I use plates. So in this case, I didn't observe strong size effect that can be definitely present for some micron wires. So thank you for your question.
The other question I have is shape memory alloys often exhibit Mullins effect or Patrikeev-Mullins effect, where with consequent cycling, typically during the first cycle, the stress of the Martensite transformation plateau is higher compared to the consequent tests. And in your data, you showed stress strain curves or load strain curves to failure. How many cycles did you try when you were looking for when you were doing the testing?
So yeah, you're right. If we take superelastic nitinol sample and then test it in cyclic loading, so we will have some hysteresis, some shift of this curve. But here in this research, this test was done in the framework of other projects. So I also see this effect for the samples manufactured by laser powder bed fusion. But in this research, I tried to compare the S-built samples by irrecoverable strain. So in this test, I used only one cycle and then immediately measured the recoverable strain. But also, as a future work, like multiple cycles can be presented to measure this value. In literature, most often, the curve will be stabilized after 10 or 15 cycles.
So do you have this capability using Instron or whatever instrument you use for the cyclic testing?
Yeah, we used Instron for that. As far as we don't need many cycles, so we do not speak about tests when we have 10 to the power 6 number of cycles. We can use just a classical Instron machine and DIC system to track the deformation for that.
Okay, thank you. My last comment, I guess, would be on the thesis and in your slides. When we had discussion in Skoltech in the summer, I pointed out that you use abbreviation for the arbitrary units as A.U for your X-ray diffraction, and also on slide 23, I believe. And typically A.U stands for atomic units or
yeah, it's better arp.u. Yes.
Right. So that's my comment for the formatting of your thesis. Just you know, it's not really a big deal, but and it's understandable, but it's probably better if you correct it.
Okay, thank you for your comments.
Okay, thank you
I
very
have no-
much.
I have no other question.
Okay, are you satisfied with the corrections that were made to your comments, or its response to your comments?
Yes.
Okay, thank you very much. We'll now go to Professor Ivan Sergeyev for his questions.
Thank you. So Stanislav, I have one principal question. So you say that you theory the functional properties of shape memory alloy, but at the same time you spent a huge amount of work and experimental study and comprehensive simulation work in terms of material science. And at the same time, there is no significant study of functional behavior of the self-adjusting files that you used as a demonstrator. So therefore, it seems like this principal thing is omitted in the thesis, and I'd like to pay your attention to this thing. So because of, once again, you, I think it's obvious for everybody that you perform very comprehensive experimental and simulation work for material science. But actually, if you point to tailoring of the functional properties of these shape memory alloys, so therefore you need to justify that your method, your technology provides required functionality of the self-adjusting files that you used as a demonstrator in your thesis. So thank you.
Yeah, thank you for your comment. So first of all, I want to say that functional properties in terms of NiTi, it's mean shape memory effect or superelasticity. So by tailoring the functional properties, it means that we can locally control the temperature of the shape memory effect. So the temperature when shape memory effect appear, or we can receive superelasticity in the as-built condition. So in terms of control of the temperature for shape memory effect to appear, actually this experiment was performed. So it was demonstrated experimentally that different part of the same sample manufactured by laser powder bed fusion can exhibit different temperatures of shape memory effect activation. So that's mean tailoring of functional properties. What you think about the self-adjusting files, correct? So this work is still running, right? And for the files, we actually need to have not shape memory effect, but superelasticity. So when this file go inside the kernel, it deforms. So it adapts itself to the geometry of kernel, and once you eject it from the kernel, the geometry of file will be recovered because of superelasticity. So no heating as it is for the shape memory effect. So I hope I answered your question. So the functionality of the NiTi files that manufactured by LPBF will be further analyzed in the further work. So thank you.
Thank you.
No question. Are you satisfied with the changes that?
Yes, satisfied.
Okay.
Thank you.
Thank you very much. Professor Evlashin, your turn.
Yes, thank you for interesting talk. So I have a few questions. One question for me, it's not clear how influence of grain size and orientation of grain size of the mechanical properties of printed materials, because mainly you study only one orientation, vertically oriented samples. But it's also interesting to study what will be if you change the grain size and print the sample in another direction. And this is first question. And maybe I continue and give some remarks about second one. So from experimental part of the work, it's clear for me, it's really good results, but from theoretical part, it's not clear for me, because if we look on the vapor pressure for nickel and titanium, we easily realized was, of course, nickel will evaporate earlier.
Yes.
For why you decided to conduct this study? Because you can estimate this effect by analyzing the vapor pressure at different temperature.
Thank you for your questions. So first question that is related to the grain structure and orientation of sample. Yeah, you're right. So if in laser powder bed fusion technology, we actually can achieve equiaxed grain structure when the grains are not highly elongated along the build direction. But for the thin-walled samples that I work on, actually the heat sink from the melt pool is quite limited, because the only solid part that is presented below the melt pool is the previous layer, which is 100 or 200 microns thick. So when we print volumetric parts, we can achieve more like equiaxed grain structure. The heat sink happen not only to the directly previous layer, but also to the XY directions. So regarding my experience with thin-walled samples, all samples were received with highly pronounced texture in the building direction. So good idea for further analysis of these micro objects manufactured by laser powder bed fusion is to put these walls into the other orientation. So in this work, it was studied the building direction, and we obviously have the second one. And I at the start of the research, I actually printed both types of samples, but as far as I didn't see big difference, I switch only to the vertical orientation. But I think that maybe some effects can appear for the other orientation. So this can be concluded for the work continuation. Another question was related to the, as I understand, to the motivation of complex simulations, why we would perform such costly from the computer time simulation if we can take the saturation pressure and analyze the difference. No, we can't, because the many complex phenomena happen inside the melt pool during laser powder bed fusion, and the temperature distribution, the surface area of liquid domain from which particles are evaporated, it's all completely different in the broad window of process parameters. That's why simple evaluation, well, it can be performed, this evaluation based on some Rosenthal model. For example, Rosenthal model allow you to analytically calculate, evaluate the temperature inside the melt pool based on your heat source. and you can couple it with saturated pressure and evaluate what will be the kinetics of evaporation. But it wouldn't give you sufficient accuracy to speak about like 0.1, 0.2% of nickel depletion. So that's why such simulations was performed.
Okay. I'm satisfied.
Okay, you're satisfied with the answers and the
Thank you.
changes? Okay, thank you very much. I have two small questions.
Yes.
The first one is, what is the minimum thickness of the parts of, because you have very fine structure there in the stent. What is the minimum size that you can go to?
Yeah, this is a good question, and I wouldn't like to answer it by one number, because actually the thickness of wall that can be achieved by our laser, which have 55 microns of diameter, so we can actually achieve comparable thickness of wall or comparable thickness of strut in such latest structure, I would say. But these objects will have poor metallurgical contact between layers, so the mechanical properties will be really bad. So if we're speaking about the interplay between the sufficient melting and the need of high resolution, we can achieve the strut of from 120 to 150 microns, I would say. But according also to some experience, it would be even better to achieve high quality micro device by applying more laser energy, and then apply chemical etching to this part. So in this case, we will decrease the roughness of the surface. So in eventually, during the process of melting, we will have adhered particles for each surface of our part. And if we do not need such surface, rough surface, it would be required to apply some etching. So my answer is 150, but maybe it's better to go even another way.
Okay, thank you very much. My second question is quite simple. You show some diagrams and you mentioned it, and there was the grain size question. And I see that you have some diagrams with 0.1, 0.2% change in this one, and with important change in the parameter. And is this possible in given the grain size, to control the percentage of nickel in the pool?
Yeah, thank you for this question. Yeah, this is the main dream of the entire research, to locally control this temperature of the transformation because of this evaporation. And basically, yes, it can be controlled, but in really small range of process parameters. Why? In this research, I utilized a broad window of process conditions to have a big difference from one to another. But if we speaking about some optimal conditions, in this optimal window, the change of nickel will be lower. So I would say that it is possible, but not in a wide range as it was demonstrated in this scientific research. For real application, this will be this difference will be lower.
Okay, thank you very much. I'm satisfied also with the changes. Now we'll go to the audience. Professor Korsunsky, Professor Salomon, if you have any questions or comments, you're welcome.
Thank you very much, and thank you for presenting an extensive and thorough study. I couldn't quite understand decide for myself whether it was mostly a material science study or a technology optimization study or a modeling study. Let me explain what I mean. On slide 40, you say microstructure. Not 14, 40. Mm-hmm. You studied in MISIS, didn't you?
Yeah, correct.
So if you said to somebody that that's your picture of the microstructure, they'd say, "Are you joking? I can't quite see. You didn't etch it to see the grains. You didn't do EBSD to see the grain orientation contrast." So it's an illustration of something. Some things are in contrast, some things are without contrast. In fact, as you may have seen from some reference work and recent work, another aspect that affects the shape memory effect and the superelastic effect is the microstructure, is the texture. So without taking that into account, your claim to control the temperature by manufacturing cannot be complete. If you say, I run this and I know that by composition I can vary it, that's fine. But if there is another parameter or several parameters which also affect the performance, then you can't ignore them. Then another thing that I couldn't quite understand, there is a lot of activity going across the board, people trying to learn to model predictively the process of additive manufacturing. I just felt that it wasn't made sufficiently clear. You said that you're using some sort of framework, and you said that it requires certain parameters. You put them in, it simulates something. Is that it? I mean, your thesis at the core is devoted to you using a software package that somebody else wrote in order to see what it predicts. Is that it?
So should I answer the first question and then second?
The first was a comment. The second is a question.
But I would also
if you feel that you have something to counterpose, by all means, you might get.
Yeah, because this is really a good comment, because in a publication there is claim that microstructure definitely change the transformation temperature and so on. But if we look through it even deeper, we can see that the dependence of transformation temperature from chemical composition is much more stronger than in comparison with microstructure. And this is just an illustration of the texture that I received. This was your another comment. Thank you. So about the second comment. Simulation of laser powder bed fusion is quite complicated tasks. So during thesis, I also implemented my own solution of the problem. I used Kamzol, where I put all my knowledge about this simulation, and I made some. I used some double ellipsoid heat source to simulate the simulation, but to involve every process of fluid dynamics, of evaporation and Marangoni effect, it's quite a complicated task inside one thesis. So yes, I used solver that was developed by Kintec laboratory, and together this software was even further developed in terms of this task, so big component evaporation. So that's why I made more emphasis during presentation on the evaporation, but didn't really touch the fluid dynamic solver, I have the equations in the thesis that this solver used, but it was developed by Kintech laboratory, and I thanks the colleagues from this.
Thanks for that clarification. I just feel that if the I don't know this software and I have no reason to doubt it or criticize it, so don't get me wrong. What I can see as illustrations of output from that software is lifelike images. It looks believable. One of the problems with modern software is that people are so good at producing something that looks believable that you don't know whether it's the reality or fake news, right? I repeat again, I'm not saying that this is the case with this software. I have no basis for saying that. I'm just saying that if you use it, it would be nice to compare it, at least to a certain extent, with your experimental observation. For example, it shows certain droplets on the surface, it shows certain degree of roughness, it claims implicitly that it can predict it. And I'm just wondering to what extent, this is just one aspect. Thank you for opening that page. That's just one aspect, right? The shape of the melt pool, which is fair enough. But the question is, how far does one need to go in this direction if the geometry doesn't quite agree, even after all the attempts to calibrate it?
Sorry, the calibration procedure is completely different. In this software, we do not calibrate anything. So we have only thermal physical properties known from literature or experiment. We use them in the equation, and then we calculate the temperature fields, the velocity field inside the melt pool, and finally we obtain the cross-sectional view.
So you don't perform closed loop optimization, you prefer to believe the literature data, and even if the literature data leads to a result that doesn't agree with your experiment, you still insist on believing it. Is that what you're saying?
No.
You don't feel tempted to adjust it to get a better agreement?
In terms of comparison of the experimental and numerical results, actually on this slide the convergence is good. Because
you say it's good. I don't particularly like it. Maybe it should be quantified somehow so that we don't remain at the level of emotional reaction, right? I mean, you can introduce some sort of measure of depth, width, which you did elsewhere in your thesis, and then you can compare how well. Yeah, on the left is not so good, on the right is pretty good, not always. Yeah, we agree, no?
No, if you expect that you can achieve like 5% or 2% accuracy with simulation of such nonlinear process, it's wrong. So
okay, so what's the purpose of your simulation?
My purpose of simulation to calculate what will be the nickel depletion in thin-walled samples.
Okay.
So this
so
study
is in your case 5% enough?
In my case, I believe that such convergence is enough to move further. Yes.
Okay, so thank you for this discussion. I think my feeling is that I wouldn't be so confident in saying that 5% is enough, because my answer would be it depends. It depends on the application. In some situations, it's perfectly fine. In other situations, it's fundamental, because, of course, you are showing a measure of convergence based on some chosen parameters. There may be other parameters where the disagreement is greater, and then you need to go back. So that's fine. My final comment, because I don't want to take any more time, is this. You were moving it towards an application for these self-aligning files, or whatever they're called. So my firstly, only in the discussion it emerged that your main concern there is not the shape memory effect with which you spent most of your thesis, but actually the superelastic effect, in which case perhaps you should have focused on that more. And actually, the stress strain curves that you showed didn't go quite as far as full superelasticity, right? So that's, and the second thing is, if you are looking at the way it aligns itself with the dental canal, it would be nice to see some tomography. Because that's what you do. If you insert something and you want to check how well it conforms to a specific shape, then that begs for it. But I understand that there are limitations of access time, etc. But just a comment. Thank you.
Yes, thank you for these valuable comments.
Thank you very much. Professor Salomon, do you have a question?
Thank you very much for the opportunity to ask questions. I know Stanislav for quite a long time because he was one of my students in another place. So he's good guy and a good professional. But the point is that I was also a member of individual doctoral committee of him, so I know his work, and I have very simple and specific question. So I'm impressed of simulation. I partially agree with the criticism by Professor Krasunsky, but I do agree that the simulation is a strong part of your thesis. On the other hand, you afterwards, or you claim that you used some optimization you use some simulation data, or at least outputs for optimization of your self-adjusting files. Yeah, yes. Is it correct?
No.
No, you didn't use.
No.
Okay, so let's.
You're speaking about the very last part that I added.
Yeah, exactly. Because
no, it's not about the optimization. Sorry, I should make it clear before you continue. So this diagram was built on top of only experimental results. So
okay. I mean that. Nevertheless, there is a part 5.4 simulation of layer-wise consolidation, and you go back to.
Yeah, this was this simulation was performed just in the end of the work, and actually we think so. If we can make such a multi-layer simulation, which is actually not often performed in literature, we can even try to take the data file from our machine, where we have all the vectors for laser movement, and take this information to our software. So the laser beam, the heat source during the simulation moved as in the experimental setup. And we just tried to perform this simulation of many layers. And this was not for optimization techniques. This is for some future works where we can evaluate some local features of such structures, but by simulation. But in the framework of this research, it was not performed. So optimization was done based on only experimental findings.
I'm not pushing on optimization. I'm just trying to say that here in chapter 4, you are simulating track on a solid substrate, so solid surface. While here you have a sort of piece by piece, voxel by voxel construction, which of course is totally different field thermal history. So, and the simulation of this should be made in another way, I guess. What do you think?
No, I also need to clarify this. So, as in the case of multi-layer simulation of thin-walled samples, the procedure was completely the same. And actually, the single-track experiment was also performed on the powder layer. So we had powder and then substrate. So for thin-walled simulation, we have powder, then we remelt it, form another layer, and the same procedure was done for the
Perfect. But
SAF.
this is not a thin wall structure. This is the tubular structure.
How is it?
Tubular. Do you agree?
Okay.
Hollow.
Okay, and what it changed?
Well, this is my question. Does it change something for you?
No, because actually the heat sink at the micro level, at the scale of the melt pool, as it is in the thin walled based type, and as it is in this type that you claim, is just the same, because the heat sink is happen only from the melt pool to the previous layer. So this situation actually is quite close, thin walled one and this one.
Close, yes.
Yes,
The
close.
question is how close is it? Anyway, thank you very much.
Okay.
I'm satisfied. Okay.
Okay, thank you very much. Any other question from the audience or online? No? I will give a last chance for questions to the jury members, online or in room. Do you have any other comments or questions? No?
I'm sorry, I had a question. I typed in the chat, but maybe you haven't seen it. So maybe
No, we haven't seen it.
may I ask a question?
Yes, please go ahead. Please go ahead.
So thank you very much for your impressive talk. I have also a question about the simulation. You claim that you have a bunch of effects to taking into account, like powder spreading, like evaporation, like fluid dynamics, and so on. And we know that it's quite a complex task to simulate. So I have a question about how much time it is you need to simulate a single track or thin wall, and even this multi-layer. Maybe it makes things more clear, because we don't know. Maybe it is about weeks or months to simulate. So please clarify this.
Thank you. Actually, I want to introduce the speaker. It is Boris Korneev from Kintech Lab. And actually, this is a good advertisement, because such complex task, such complex simulation was performed, and it takes for a single track about from hour to 4 hours for a single track, and this result is quite good in terms of the simulation software. But regarding the multi-layer simulation of thin walls, or even a file, it takes a lot of time. So, and actually it depends on the scanning speed of laser. As far as this speed decreases, the simulation time increase. But in average, the multi-layer simulation was performed during a couple of days, from 4 days to 7 days. But this file actually take maybe 2 weeks to simulate. So yes, thank you for your question.
Thank you very much. We will now go to, if we're finished with questions, we'll now go to the supervisor for comment about the candidate.
Yes, hello everyone. I'm glad to see you together. As already discussed during these sessions, problematics of the NiTi three-dimensional printing and its following promise by technical features. It's a very highest interesting topic for research. I would like to emphasize that his dissertations, it's a complex because of its combine both experimental and numerical studies, which it's very useful and valuable. What's about the candidate? During his postgraduate student, Stanislav Chernyshikhin has developed as an independent researcher, capability of conducting independent project. I hope he will a good scientist. He took an active part in scientific project and grants of our laboratory. He has worked on a number applied project, and he also exhibit excellent public speaking skill during a number of presentations made him during Young Researcher Conference. In every instance, he was demonstrate a very good grasp of a subject matter and its applications hard scientific problem. Personally, Stas is extremely easy to get along with him. He support our people in our laboratory and high competitive persons. So I wish his all success in future research and in future career. Thank you for your attention.
Thank you
Thank
very
you.
much, Professor Shikovsky. Okay, so now I will ask the people to leave for the deliberation with the, and I will leave Elena, if you give us the procedure.
Thank you, Professor Fortin. So
Stanislav, a pleasure. The jury unanimously passed as is, so everyone is satisfied. Great work, and obviously the questions that I see there, whether it's material science or technology or simulation, it's kind of a good sign because obviously it's a lot of work and great work. So congratulations. And your pleasure.
Thank you.
Very good.
Yeah, I just say a few words.
Yes, a
that,
few words.
This is quite interesting moment because the period of PhD study finished. It's even a bit sad because it was one of the funniest periods of my life. A lot of interesting work was made, and I want to again thank my supervisor for this opportunity. And finally, thank you everyone who came to this defense in the audience, in the online meeting. So I hope you all are doing well. Thank you.
And thank you very much, everyone and the jury members for being with us, and we really appreciate your contributions. Thank you very much.